conference every year until the end of time. So all in favor? All opposed? Okay, would someone tell Ron about that when he comes in? Okay, thank you. All right, so this is, I hope you will find this to be an enjoyable talk. It's a departure from some other applications of ferroelectrics that my group has been involved with. I think it's really a very interesting idea, and so I'm going to be telling you about some ultra-fast electric field control of giant temperature change in ferroelectrics. This idea came out from some experimental observations of our friend and collaborator Aaron Lindenberg and an extremely talented graduate student, Yubo Chi, and a former student, Shi Lu. Now, Yubo has also graduated and is a postdoc with Karen Rabe at Rutgers, and Shi Lu is right here as part of your home team. Basically, we all know that there are Landau-Ginzburg relationships that relate temperature and polarization, and we're accustomed to changing the temperature of a ferroelectric and seeing it go through a phase transition, but this relationship can be inverted. The cartoon here is that you have a material with a certain polarization, you apply an electric field, maybe even a transient electric field, and you change the temperature and you change the phase. So we're going to talk about that in some more detail as the presentation progresses. Okay, so the electrocaloric effect is the word for this phenomenon where as you change the structural phase of a material through orienting or disorienting dipoles, you can change the temperature. And so, as I said, we may be more familiar with the pyroelectric effect because all ferroelectrics are surely also pyroelectric, and there are many other interesting pyroelectric materials out there whose polarization change with temperature. But the idea is that if an atom's getting its bond valence by summing up the bonds of its neighbors, maybe it likes that all those bonds have a vector sum of 0, or maybe it likes that it has some asymmetry to its local environment, and that can be input with this term. And then finally, we had a small angle potential that if some of the octahedra in the model without this term have too large or too small octahedral rotations, there's a fine-tuning that can be done with a single parameter here of how much the octahedra like to rotate. Okay, so this is a little bit more in depth about these potentials. So as I was mentioning, this is the way we calculate the bond valence. It's the sum of the individual bond valences, and that is an inverse power law of the distance between each atom and its nearest neighbors. And then we get the energy of the bond valence as its deviation from its prototypical valence. Okay. And then this bond valence vector, you can see an example here that if we calculated bond valence for water, it might have two perfectly good OH bonds and be happy, and here it might have two perfectly good OH bonds and be happy, but it wouldn't know that water actually wants to have a bend structure unless you reward having the sum of the two vectors be non-zero, and so you make a minimum around some value that would allow water to know that it should have a polar and low symmetry shape. And so that's been quite successful for us. Several students have contributed strongly to the methodology of bond valence, including both Yubo and Shi. So you will see some of the methodology work implemented here. Okay, so one of our recent successes is getting this bond valence model to work for barium titanate. It's a prototypical ferroelectric material, but it has all the phase transitions from rhombohedral to orthorhombic to tetrahedral to cubic, and so it was fairly difficult to do. And so there was some simulated annealing in which you take parameters and do molecular dynamic simulations and then check with density functional theory whether the energies and the forces agree well, and if they don't, then you can use additional structures to refit until you're happy with the parameters. And these are just the parameters that I mentioned to you, the prototypical bond lengths between the cations and oxygen, the charges, the short-term repulsion parameters, and so forth. Okay, and so as you can see here, the model is able to reproduce all the phase transitions, showing that you have equal polarization along X, Y, and Z at low temperature, then one of the components drops to 0, and the second one drops to 0, and then the last one drops to 0. So this would be the Curie temperature. So the temperature is all too small compared to experiment, but many of the local structures appear to be quite accurate. And it actually, the point is it's designed to reproduce first principles calculations. It's not fit to experiment. And if you do molecular dynamics with density functional theory, you would also get similar suppression of Curie temperatures. Okay, so now we can show you computational experiments relating to the electrocaloric effect. And so each of the slides is a little different, so I'll tell you about it in some detail here. So the first thing to look at is we have done an equilibrium run where we let the atoms respond at some temperature for some amount of time, and they're just all thermally moving the way they might wish. So then here is the electric field in kilovolts per centimeter, and you see for some time it's 0. There's actually quite a lot of equilibration before 0, but at some time we start to increase the electric field. Can you see? Going up linearly, there's a linear ramp, and then we leave it at some finite value. Okay. And the potential energy actually goes up. So this is what I was saying to you. This is a negative electrocaloric effect. You may have expected that as you apply an electric field, you orient the dipoles, making the potential energy go down. But in this case, the electric field is applied along the 110 direction. You see up here? And if you start in the rhombohedral phase, this will favor polarization along X and Y, and that will send a signal to the material to scramble its Z polarization. And that's what happens. So you watch the polarization as a function of time. X, Y, and Z are all finite, but then upon experiencing this electric field along the orthorhombic direction, it becomes orthorhombic. And so that is a consequence. The biggest consequence is losing this Z component of polarization. The X and Y go up a little bit along the electric field direction. So you can think of it this way. As a function of temperature, the rhombohedral potential energy is lower than the orthorhombic, but as you apply electric field, you're driving the system to higher potential energy and lower temperature, and it's crossing over to the orthorhombic state. And so you see a change in temperature of about -1 Kelvin as a result. Okay. So now this is going to examine negative electrocaloric effect in the transition from tetragonal to cubic. And so here, the electric field is applied along the y-axis, where the polarization is along the z-axis. So the electric field is perpendicular to the polarization. Okay, so now here is the electric field trace. It's different from last time. So we have our equilibration run where the electric field is 0, and then we have the electric field go negative, and then positive, and then back to 0. And this serves to scramble the electric dipoles quite effectively, that they don't have time to, in an adiabatic way, rotate and follow the electric field, because by the time they do, the electric field is the other way, and it has the consequence of just convincing the individual dipoles to scramble. And so if we make a graph of the volume average polarization along the X, Y, and Z directions, here it's tetragonal with polarization along Z, it starts to rotate into the Y direction, but pretty quickly it all scrambles, and it goes to the cubic local minimum in free energy, as opposed to finding one of the tetragonal variants. And so this leads to a change in temperature of more than 2 Kelvin. Okay, and then finally, if you look at lead titanate, we know lead titanate has a much higher TC and a much larger latent heat. And so all these phenomena apply rather similarly, but the energy scale is just significantly larger. So here we exhibit a different case. This is just for exercising the ideas. Here we apply an electric field that's anti-parallel, but it's timed to be short enough that it doesn't allow the polarization to follow. So the electric field is 0, and then we have an anti-parallel electric field for a short time, and then it turns off again. So a half-cycle pulse. And the temperature is constant, and then it drops significantly right around the time that the electric field is being applied, and the polarization goes to 0. So we have driven the system from the tetragonal phase to the cubic phase, and it's significantly lower temperature. And it's supercooled in the sense that at this temperature, it really would prefer to be in the tetragonal phase, but it doesn't know that. It takes time for nucleation and growth to reassert itself. Okay, and so here is a short but nice movie of this. So this is the case of tetragonal barium titanate. Do you see the dipoles are pointing up, but the electric field is applied along the horizontal direction. Okay, so they're undergoing thermal motion, but then some of them are starting to rotate. You can see that there's just a greater disorder in the dipoles, but some of them are visiting, being 90 degrees away from the original direction. And as this happens, the temperature is dropping the whole time because the potential energy is rising. They're not aligned. They're not nearly as aligned as they started. And so this is ultra-fast negative temperature change induced by electric field. Okay, good. Oh. Okay, there we go. Okay, so the basic idea is if you have a Landau-Devonshire model of the energy versus polarization, for very low temperatures, it's a double well. We're very familiar with this. You have maybe up polarization and down polarization. But if you get near the crossover between the polar state and the nonpolar state can be a local minimum. It's not favored, but it can be a local minimum. And then eventually you get to a high enough temperature that the minimum at zero polarization is the absolute minimum. And then you're in the paraelectric state. But there's this crossover region where you have accessible to you states with significantly different potential energy. And that opens this opportunity for using the latent heat. And so schematically, what we're doing with this electric field is we're driving the polarization away from its favored value, and for certain pulse shapes and durations, it can become convinced that the closest minimum is the p equals 0, 1. It'll fall into that minimum and stay there for some amount of time. And depending on how close we are to the temperature at which the zero polarization minimum goes away, or becomes dominant over the positive polarization, that sets the time scale over which this can be metastable. And in order to have such a Gibbs free energy profile, we have temperature near the Curie temperature. Not below, but not quite, not too far away. And the electric field profile should be properly designed. Okay, so what have I presented to you today? We talk about the electrocaloric effect always from an energy point of view. As I say, my friends often talk about entropy redistribution, and I think that everything I told you about today can be worked out in that language. But it turns out that you can lose track of some energy when the system is not maintained at quasi-equilibrium. And so we think this energy point of view allows you to really understand what you're doing better and more simply. And to get large temperature changes, you need strong ferroelectric systems with a large latent heat. And the electric field profile can either be perpendicular to the polarization, anti-parallel, or in the third case that I showed you, you can apply the electric field in a way that encourages some components of the polarization, but not others, selectively removing one component of polarization. All of these are possible. And the largest energy change we see is that for lead titanate. And so this is a summary of some of the results, is a range of temperature changes that I showed you today. And so it's a pleasure to remind you that this was a very fruitful collaboration with Aaron Lindenberg, who is at SLAC and also at Stanford, and Shi Lu from the Carnegie Institution for Science, and Yubo Chi, who is no longer at the University of Pennsylvania, I'm sorry to say, but I'm happy to say he's now productively working at Rutgers. And so with that, I thank you for your attention, and I will be happy to take your questions.
Okay, great. So we have time for a few questions.
Andrew, I understand that the last process you discussed depends on how fast you switch on the electric field, or what is the profile in time. Does it mean that we actually transfer some momentum?
I guess you transfer a little momentum. Sure. Not a lot. Yeah. But in fact, what we're really doing is telling them to scramble. You see, they're not following the direction of the electric field. Under the influence of the electric field, the state they were in is destabilized, but then they thermally go to other states.
So, yeah.
Oh.
I mean, beautiful talk, by the way. Did I understand correctly that the first case is more of a quasi-static, equilibrium case where you tickle it from the rhombohedral phase to the orthorhombic phase by applying a field kind of in equilibrium, whereas the second and third one both require this trick of kicking it into the undercooled higher free energy state. Because it seems to me that only the first one is really useful for refrigeration purposes. Maybe I don't understand.
Oh, I think that's okay. The first part you're right. I think the second part I'd like to, at least in a kind way, quarrel with. So yes, I think that when we converted the 111 to the 110, we think that's a great thing that can be done and leave the electric field on as long as you might wish. Yes. Anytime you're trying to access the para-electric state, I think we agree that you can get the temperature to go negative, but then you're wondering what will happen later for the rest of the cycle. And I feel like we could couple a negative electrocaloric effect with a positive electrocaloric effect. We could apply an electric field that does the conventional thing of aligning dipoles and making the temperature go up. We could do negative ECE and positive ECE, and that should be just fine.
Thanks for the nice talk. So normally when you do this in molecular dynamics, this direct estimation of the caloric effect, so you should, in principle, you have to be quite slow in switching on and switching off the electric field. So for instance, if you had here a relaxo, so it has been shown that if you just do like an abrupt change of the electric field like this, you are not getting the right due to ergodicity, you are not getting the right estimation. So how that really affects? So have you checked that in your work? So if that pulls, so when really you change. So rather than doing it ultra fast, you do it a bit slower. So that the final result changes.
That's a really well phrased and erudite question. I think what saves us is we are driving the system to a higher entropy state. So even if it's in an interesting local minimum, we're raising it up out of that. And then it is ergodic at the end, you see? And so I have no concern that if we do it slower, we will get something different. But we did try a range of times. But if you say, what if you try it over a millisecond instead of a nanosecond, I think it may have enough time to nucleate and reform domains. There's only so long that these states will remain supercooled. So we're trying to beat that. So to some extent, fast is the point, and non-ergodic is the point in a way. But when we access the paraelectric structure, I think we're avoiding some of the concerns that you raised.
Thank you, Andrew. Unfortunately, we're going to have to stop there with questions to stay on time so we can have dinner at a reasonable hour. So Andrew will be around so we can take more questions. Let's thank him once again.
Okay, thank you. Good luck.